So the directions on this warm-up actually say like to graph each of them and then describe the transformations. I don't want you to use the transformations to graph them. I actually just want you to graph them. On your quiz, it's not going to be as simple as like a 2x. You're going to get a function. You're going to have to graph it. And I give you the little t-chart. So we're going to do it that way. We're going to follow that process. Yeah. All right. So I'm going to do the t-chart for f of x. We know most of this because we've done it. I would get the x and the y. You just have to plug in the -1, the 0, and the 1. 2 to the -1 would be 1/2. 2 to the 0 would be 1. And 2 to the first would be 2. And then I will plot those. So -1 and 1/2. 0 and 1, 1 and 2. This is one of those graphs that is not that obvious on the curve. It almost looks like it's a line. It's not exactly if you try to connect all three of those. But it's important to understand that you are graphing an exponential function, so you have to make that curve happen. Okay, so you cannot draw this as a line. You have to make sure that that curve goes above your x-axis and then comes up. It doesn't have to be perfectly accurate on the steepness after the 1, but you actually have to make that curve happen. So for that one, our horizontal asymptote is at y equals 0. Our y-intercept you can either get from the graph or from the middle coordinate point, which is 0, 1. Our domain is -∞ to +∞. And our range is 0 with a parentheses to +∞. So all of that is true about that parent function. Then if I graph the adjusted one, the g of x, I would still do the same thing. You want to get comfortable doing that t-chart because that's how you'll do it on the quiz. This would be 2 to the -1 minus 2, and then 2 to the 0 minus 2, and then 2 to the first minus 2. So 2 to the -1 is that 1/2 minus 2, that's -1.5. 2 to the 0 would be 1 minus 2, that's -1, and 2 to the first minus 2 is 2 minus 2, which is 0. So -1.5, -1, and 0. Now if I plot those points, -1 and -1.5, 0, -1, and 1, 0. Now my curve looks like this. And again, you need to know to make that curve, you need to know where it would bottom out, which now my horizontal asymptote just shifted down 2 places. So it's at y equals -2. Which part? Like the blue one? Yeah. The y-intercept this time, it's easier to just get it from your chart or from the whole, it's on a whole number, so it doesn't matter. 0, -1, and then domain is still -∞ to +∞, but the range also shifted down so that it's -2 to +∞. So the horizontal asymptote of the first one is at my x-axis, and the second one is at the y equals -2. Yeah. You won't do both is what I was saying on the quiz. It's just going to give you a shifted one. So could you have yes? Yeah. Especially because it was a whole number, the y-intercept. It may not be like that on the quiz. So, yeah. Mm-hmm. Questions? And then be expected to answer domain, range, intercept, and horizontally asymptote. Like all those things are going to get asked about your graph. Okay, then came the interest problems. So remember, there's 2 formulas you need to know from this. One is if it's a number of times a year, then it's A equals P times 1 plus R over N to the NT. And we're going to make sure the R is in decimal format. That's the biggest mistake made on these. You have to move the decimal 2 places left. And then if it was continuous, it's PERT, P times E to the RT. Those are not going to be given to you. Obviously, you don't have a reference sheet. Those days are long gone. So you want to make sure that I would say every time you do one of these problems, rewrite out that formula if you don't know it yet. By the time you get to Wednesday's quiz, you should be able to memorize it. All right, so number 2 says determine the balance for a $3,200 investment at 2% for 20 years compounded, and A says monthly. So which formula am I using for A? Good. P times 1 plus R over N to the NT. So P is my principal balance. That's the $3,200. 1 plus my rate is this in decimal format. So 2% is what? 0.02. Good. Number of times a year if it's monthly? 12 raised to the number of times a year times the number of years. Good. And then I let the calculator do that work for me. So 3,200, open the parentheses, 1 plus 0.02 divided by 12, close my parentheses, raise it to the power of 12 times 20. $4,772, and this is money, so we're going to round to the hundredth, 25 cents. So the percent wasn't very high, but it was in there for 20 years. So there should be a bigger jump in the price. We went from, 3,200 to 47, almost 48. All right, then continuous, we are using the PERT, right? So 3,200 e to the r, which is 0.02 to the t, or times t, which is 20. And then again, let the calculator do the work. 3,200, find the e above the ln, 0.02 times 20. And I get $4,773.84. So not much more, but it should be bigger than any other one. Continuous should be the most amount of money. Questions on any of that stuff? All right, 3.2 is logarithmic functions, okay? These are logs for short. The logs and the exponentials are inverses of each other. So if I took something like x, 3 to the x, and then I did log base 3 of x, all of the x and y values would be completely opposite. So everything we know about domain now gets applied to range. Everything we knew about range now gets applied to domain. All the things switch, okay? So we're going to learn first like how to convert from log to exponential and exponential back to log. So you can go back and forth between the two. And then we're going to get into graphing these, okay? So this is how a log is written. Y equals log. The little number is called a base. So that a is a base. And then the big number would be your of. So this would be read as y equals log base a of x. And they are interchangeable from log to exponential and exponential to log. To get from log to exponential, the base on the log comes over and picks up the y that's by itself, making it its exponent, and then it drops off, leaving the bigger part by itself. So I usually say that logs are like high school relationships. The two terms never stay together. At some point, that always offends somebody. So I am not talking about all of your relationships. Your relationship will last forever. Okay? But if you remember that the two things that are next to each other, whether it's in exponential or log form, they never stay together. So they will always part and go with the other side. So when you're looking at log base a of x, there are two things together here. I know they can't stay together. This one comes over and picks up that shiny y that looks better than the current situation. And it grabs that and it drops off, leaving that lonely little x all by itself. Okay?
Like the whole log?
The whole log will go away. So if this had said log base 2 of x equals 3, let's just say. The 2 comes over and picks up the 3. It makes it its exponent. It drops off and leaves the x by itself.
That's how you get the x.
Mm-hmm.
The a becomes the base of the other number?
Well, it's called a base, right? So in this expression, this is log base a. It's called a base there. It becomes the base of the exponential. Yep, it's that stays the base. And then vice versa. If I went from this expression, if I went from 2/3, 2 to the third equals x, again, they won't stay together. The base of the exponential function is the base on the log, so it's the little guy now. The x switches to be over here with the side, and the 3 bumps to the other side. Remember, they never stay together. So no pair stays together in your logs and your exponentials when you're converting back and forth. So if I had y equals log base b of x, the b comes over, picks up the y, drops off, leaving the x, and it looks like this. Okay, they have to be true statements. So if it is a full numeric statement, it has to be true. Like 2 to the third is 8. So then the base on the exponential function becomes the base on the log. The 3 goes to the other side, and the 8 switches positions to be with that too. All right, so first thing we're going to do is just rewrite the equation in exponential form. So this starts as log 4 equals log base 2 of x would be what in exponential form? Good. Eventually we will solve these, but for right now we're just rewriting. Then x equals log base 3 of 9. 3 comes over, picks up the x, and the log drops off, leaving the 9. Now we go the other way. So now we're starting exponential. We want to put it into log. So b to the 4th equals 16. b is the base. So this becomes log base b. The 4 goes to the other side. The 16 joins the b. And it would be log base b of 16 equals 4. 5 to the 2nd equals x. This would become log base 5 of x equals 2. All right, so this one says evaluate the function at the indicated value of x without using a calculator. We will get into the ones in which you have to use a calculator. They are not yet, okay? So A is f of x equals log base 4 of x if x is 64. So I would just do log base 4 of 64 equals, and I can replace the f of x with y if the f of x bothers you. We are going to get so good at these will become mental math. They will become fast and require very little work. So people who love that stuff usually enjoy logs, okay? But we're going to baby step our way into those. So the 4 comes over and picks up the y. 4 to the y equals 64. And then you're either saying, what do I have to raise 4 to get to 64? Or you change your base like we did yesterday and set your exponents equal to each other. Either way, it doesn't matter, okay? But these, without a calculator, will always be something that can be raised to that power. So what can I raise 4 to get it to 64? 3. So my answer is just 3.
Not what equals to.
It doesn't matter. Yeah, because sometimes you're going to have the f of x equals and sometimes you're not. So look. So the 4 came over, picked up the y, right? You're good with the exponential, the log to exponential?
Yeah.
So then what power do I raise 4 to get it to be 64? Yeah. You can change the base like we did yesterday. I can rewrite 64 as 4 to the 3rd, but you don't have to continue to do that step. All right, so then here, y equals log base 36 of x. So 36, oh no, the x is now 1/6. So 36 to what power gives me 1/6? So close. So the negative part's right. It has to move, right? Half. So to get from 36 to 6, you would have to square root. Does that make sense? And a square root exponent is 1/2. So square root equals 1/2 exponent. Cube root would equal 1/3 exponent. Exponents, not just... Okay. And again, we'll get to the mental math if that didn't just click. Your other option here is rewrite this. So it's 36 to the y equals, this would be 6 to the negative 1, because I would bring the 6 to the top, right? Then I could change the base on the 36. 36 is 6 squared raised to the y equals 6 to the negative 1. 6 to the 2y would equal 6 to the negative 1, and then I can solve my exponents. Your goal is to not need to do that, though. Your goal is to get the mental math so that these are fast. So if I had 25 and 1/5, that is negative 1/2. If I had 25 and 5, it's just 1/2. So to square root, it's a half. Because it was in the denominator here, it become a negative. Don't worry, God bless you. We're going to do lots more. No, because then it would be 36. You're saying 36 squared equals 1 over 6, right? 36 squared is not 6. So 36 to the negative 2 would be 1 over 36 squared.
Oh.
Yeah.
Because when I did this, I put 1 over 6 to the negative 2.
Oh, don't do that. You can't change it. Yeah. You can rewrite it so it's negative 1, but you can't change it to be a different. Does that make sense? Yeah. All right. So now if you have your calculator, take it out. There are 2 types of calculators. Like, obviously, there's 800 different types of calculators, but there are 2 different types in terms of how we type stuff in. Most commonly, I would say, is the right-hand side, but it doesn't mean they're all going to be this way. The right-hand side means if you hit the button that says log, it's above that e to the x one. Do you see the word log appear in your screen? Yes. If that is you, then you're doing the order on the right-hand side. If I wanted to find log of 1,000, I would literally hit log, and I would hit 1,000, and I would hit enter. The log that is in your calculator is base 10. So it only works this way if the base is 10. So just the word log by itself is the same thing as log base 10. And that is the one your calculator has, okay? There is something called change of base, which we're going to get to, and you'll see that in a little bit, where the log is not, the base is not 10. And some calculators allow you to change it, but not all. If when you hit the word log on your calculator, you got 1 as an answer instead of log, okay? Then you're the left side of this screen. You have to first type in 1,000, and then you have to hit the log. So that would be your phone, would be that kind, okay? The simple, the scientific calculators that when you, again, same thing. When you hit the word log, it does not appear. It actually is computing log of whatever was there first.
Does it matter if my calculator's in degree or radian?
No, not till we get to trig will that matter. So when you hit sine, cosine, and tangent buttons, that's when that matters.
Which one should it be in?
It should be in well, I mean, right now it doesn't matter. It should be in degrees. Yeah. Well, next chapter, that will be important. Okay. So if I had log of 5 halves and I wanted to find that log, then on your graphing calculator, you will do log, the parentheses will open for itself. You would do 5 divided by 2, and you should get 0.39794, so on and so forth. If you are using a phone or one of the simple scientific calculators, then you would do it in the reverse. You would do 5 divided by 2, and then you would hit log. If it's log of 5 over log of 2, then you have to do log of 5, close your parentheses, divided by log of 2, and you should get 2.32193, so on and so forth. And then if you're trying to find log of -3, you should get on the graphing calculators, it says error, non-real answers, quit or go to. Because think about what you're trying to say. You're trying to say, if this was base 10 and this is -3, and I'm trying to figure out what it is, so I could either set it x or y. I'm saying, what power do I raise 10 to get it to be a -3? Can you ever have the result of a log be a negative number? No. The base, this will always be positive or 0, but it will always be positive. And there is no value you can raise it to get it to be negative. So the answer of a log equation can never be negative. All right, this one says use the calculator to evaluate the function of the indicated value of x. So I'm going to type in -3 log of 2.7. -1.294. I didn't say what to round it to. Round it to 3 points. So nearest thousandth.
Wait, you don't have to do the 10?
The answer, because it's being multiplied by a -3, can be negative, right? This can't be negative, but we multiply by a negative. Yeah.
Like the in the parentheses cannot be negative.
Correct. This can't be negative because you're saying something to a power equals a negative number. That can't be. But when we multiply by a negative at the end, it
Why
can be.
can't we move the 10? Like
Because log is log base 10. Those are the same things.
So we don't move anything when it's 10 at the bottom?
No, you're literally, no, it wouldn't matter if it was 10 or not 10. You're plugging in here. So you're literally just doing this statement.
So we do this, we round.
Yes, and your quiz will tell you there's really only one part where you're rounding on your quiz. And it will tell you what to round to. There's two. It will tell you what to round to. You're welcome. All right, so here's some properties which again help with the mental math. Log of any base of 1, so if the big number here is 1, the answer is 0. Because if you think about it, the only way to get a base to raise to a power to give you 1 is if you raise it to the 0 power. So if I had log of 7, 1, that answer is 0. If I had log of 725, 1, that answer is 0. So if the big number is 1, my answer is 0. Because anything to the 0 power gives you 1. Log base a of a equals 1. Because if the base and the exponent, or the base and the one in the big spot are the same, we're saying keep it the same. How do you keep something the same by raising it to a power? You raise it to the power of 1. So if I had log 7 of 7, that answer is 1. Log 725, that answer is 1. So if the little base and the big number are the same, then my answer is 1. This should be a to the first, like that. That 1 should be up there. Then log base a of a to the x equals x. So if you have something in your base, like 7, and then you have that same number and it is raised to a power, the long way around it would be to set this equal to x, let the 7 come over and pick up the x, drop off and leave you with 7 to the third. The bases are the same, so the exponents are the same, and this would be x equals 3. And you can do that every time. But the shortcut is if the base and the big term are the same, we keep, and it has an exponent, you keep the exponent.
Like the exponent's the answer.
The exponent is the answer. And the reverse of that, if you have an exponential function and the big part of the exponential function, so the base of the exponential function, and then the exponent has a log in it with the same base, then I literally cancel through all of it and keep what's next to it. So that would look like this. 7 log base 7 of 3. So the base on my exponential function and the base of its exponential log cancel. And this answer would just be 3. And again, you could set it equal to x, go a long way around, convert it into log, and then use your one-to-one property to solve it. But the faster you get at these shortcuts, the easier it's going to be. Okay, then the last thing is the one-to-one property dealing with logs. So if I have log with a base and log with the same base on either side of my equal signs, they have to be the same base, then I can literally set what's next to it equal to each other. So if I had log of 3 of 10 equals log of 3 x plus 2, then I can literally say 10 equals x plus 2. And x would be 8. So the log has to be on both sides of the equal sign and the base on the log has to be the same in order for that to work. All right, look at A. Solve the equation for x. So log base 3 of 81 equals x. We'll do long way around and then we'll eventually get to be able to do this in your head, okay? 3 comes over here and picks up the x. So 3 to the x equals, this drops off, 81. Now again, for now, these will always be some sort of power to work out. So if you don't know off the top of your head what power I have to raise 3 to get to 81, then I break 81 down, right? If I did 3 and 27, or let's go with what with what your brain would probably have done. 9 and 9, which is 3 and 3, and 3 and 3. How many 3s are there? 4. So this would be 3 to the x equals 3 to the 4th. And x would equal 4. Some of these you should get to know so well that you can do that in your head. Like I would say no 3 up to the 4th, no 2. I mean 2 you could go a while, but 2 up to the 5th maybe. 4 at least to the 3rd. Those things you're going to see a lot. 5 to the 3rd. Like all the cube roots. Those are pretty common. All right, then 5 comes over and picks up the x. Drops off, leaves you with 1. So 5 to what power gives you 1? 0. Questions so far? These are fast though. Use the properties of logs to find the answers. So look at A. 3 to the log base 3 of 15. What's the answer? 15. B. Log base 2 of 2 to the 3rd. 3. C. Log base 9 of 9.
1.
Good. And log base 3 of 1/3.
-1.
Good.
Wait, how do you know it's wrong?
Which one?
Negative one.
So these are the same.
No, negative one.
The negative.
This one, so if they were the same, right? So there's a lot of different ways to look at it, right? But how do I get 3 to move to the bottom of a fraction? I don't want to change the value, so my number's going to be 1. But to move it, it becomes -1.
But could you make it equal to x?
Yep. If you don't see it, make it equal to x. Convert it to exponential. Write it so it has the same base. And then set your exponents equal to each other. Yep.
Could you explain A? I don't understand how you got 15.
So the long way around it would be to take that as an exponential function and rewrite it as log, right? So I could say that this equals x, and the 3 becomes the base on the log. It would be log base 3, they separate, of x equals the exponent, log base 3 of 15. And then because log base 3 is on either side of the equal sign, I can use the 1-to-1 property to solve, and it would get x equals 15. But you don't want to go through all those steps. You want to be able to look at it and see that if this is the base, and it is the same as the base on the exponential log, they cancel out and leave you whatever's left. Same thing with this one. Like I could have set this b equal to x. I would have done 2 to the x equals 2 to the 3. The bases would both be the same, so I set the exponents equal to each other. But the base, if the bases are the same, whether it's the base on the log and the base on the exponential this way, or the base on the exponential and the base on the log this way, they will always cancel out and leave you with whatever's left. There it's the 15 and there it's the 3. All right, now we're going to graph them. So the good news is it's very similar-ish to exponential, except that everything flip-flops. So they are inverses of each other. So think inverses, we switch the x and y, right? I know it's been like maybe 3 weeks, so we don't remember anything from there. But when we did inverses, we literally switched the x and the y. The same thing's going to happen. So if I took and switched all the x and y's on an exponential function, it would take this exponential function, which is the blue one, and it would flip it to look like this. So our log shapes start low and work their way up to the right-hand side, the parent function of the log shapes, okay? They do not have a horizontal asymptote. They now have a vertical asymptote, so everything switches. The domain on the exponential was all real numbers. Now the range on the log is all real numbers. And the range was fixed on the exponential. Now the domain is fixed on the log. So everything switches. So we now have a vertical asymptote. I will ask you the x-intercept, not the y-intercept. And I will ask you for domain and range, but they will be switched, okay? Everything we do is just like it was with exponential, except we plug in for the y. So the easiest thing to do, and there's a lot of different ways to graph logs. I've seen a lot of different things. I've seen people graph the exponential and then switch all the x and y's. On a basic function, that's easy and okay, but once you start shifting it around, it gets really complicated. My advice is just do this. Instead of plugging in for the x value, we plug in for the y. And then you will get your 3 points, you will plot your 3 points, and you will draw your curve, okay? And then you will look for a vertical asymptote. You will look for an x-intercept, which would be the middle coordinate point on your t-chart. The domain will be based on your horizontal shift, and the range is going to be negative infinity to positive infinity. So these two things are based on horizontal shift. Where everything was based on the vertical shift with exponential, it's horizontal again, switch the x and the y's. So it's horizontal with the logs. So this example on the bottom takes the 2 to the x, graphs it, and then flips it. I would not recommend that method. We're going to do it different. This is everything I just said. So there's an x-intercept this time that we're going to look at. There's a vertical asymptote, okay? The function is increasing as you move to the right or decreasing as you move to the right if the log is a fraction, which we'll again look at in a second. It is a curve, so just like with exponential, you can't give me a line. It has to have that natural curve. All right, I'm going to talk about this after. You are figuring out your horizontal asymptote. If you think about what we did with the exponential, we looked for the vertical shift, right? The same thing's going to happen with this, except we're looking for a horizontal shift. And the horizontal shift comes from the parentheses. So the easiest way to find your horizontal asymptote and the adjustment to your domain is by taking whatever's in the parentheses next to the log and setting it equal to 0. So if it is just f of x equals log base 2 of x, then my vertical asymptote is at x equals 0, and my domain is 0 to positive infinity. If it was f of x equals log base 2 of x minus 1, I shifted it to the right one. I can set my parentheses equal to 0, and I get x equals 1 would now be my vertical asymptote, and my range would be 1 to positive infinity.
So the first one doesn't have a vertical asymptote?
It does. It's at x equals 1. So logs always have a vertical asymptote. Yep. We graph it. We're gonna graph it first. The translations work the same. If you add this time after the function, it's shifting it up and down. That will naturally happen with our plug-in points, and you're not worried too much about what happens with that graph. The most important thing with logs is the horizontal transformation, because this shifts the vertical asymptote and the domain. So this time it is 0 unless there's a horizontal shift. On the exponential, it was 0 unless there was a vertical shift. If he doesn't want to pay attention, that's on him.
No.
Oh, okay.
I missed something.
Oh, okay. Okay, I'm not going to do the exponential. I'm going to go straight to the log, because these will be separated out on your quiz and your test. So g of x equals log base 3 of x. So the first thing I'm going to do is rewrite that as y equals log base 3 of x. And then I'm going to convert it into exponential. So the 3 comes over and picks up the y. And then it drops off, setting it equal to x. And this is why we plug in for the y. If you plug in for the x, it's a lot harder to figure out what you have to raise 3 by to get to it. So this is when it's easy to just plug in for the y. -1, 0, 1. So 3 to the -1, 3 to the 0, and 3 to the first. 1/3, 1, and 3. So I have 1/3, -1, 1, 0, and 3, 1. Is there a horizontal shift here? No. So my vertical asymptote is at y, x equals 0. I would set that equal to 0. Vertical asymptote, x equals 0. Which means my curve goes as close to that axis as possible without touching it. Domain is 0 to positive infinity. Range is all real numbers. X-intercept comes from the graph or the middle point on my t-chart, 1, 0.
The name is left to right, right?
Correct. Okay. We're going to graph it by using the t-chart, and then we're going to think about what the transformations would have done to my graph, okay? So start with the t-chart. First thing, replace g of x with y, base 3 of x minus 1. Before I can convert this into exponential, I have to get rid of the negative on the front. So if there was a number on the front, I'd have to do the same thing. So I'm going to multiply or divide everything by negative 1. I end up with negative y equals log base 3 of x minus 1.
For this one, didn't we have negative though? When we were able to do it?
Yeah, but you're just evaluating that, so the
Oh,
calculator.
you're
You're just plugging in the calculator, yeah. So now 3 comes over and picks up the negative y. I end up 3 to the negative y equals, now I have this whole thing, x minus 1. Then I'd add the 1, and I end up with 3 to the negative y plus 1 equals x. That's the equation I'm going to use to plug in. So 3 to the negative 1 plus 1, 3 to the negative 0 plus 1, and 3 to the negative 1 plus 1. This becomes positive. 3 to the first is 3, plus 1 is 4. 3 to the 0 is 1, plus 1 is 2. 3 to the negative 1 is 1/3 plus 1, which is 1 1/3.
What did you write there?
Which one?
Okay, below the table that you drew there, 3 and then like what?
It's negative 1,
Oh.
so it became positive 1. Okay, there's my points. 4, -1, 2, 0, and 1 1/3, 1. Now, go back to the initial one. Here's my vertical or horizontal shift, x minus 1. So I set that equal to 0, and I get my vertical asymptote is at x equals 1.
How did you know that? You just said
Whatever's inside the parentheses, you set it equal to 1, equal to 0. Then it would just be x equals 0. Yeah. So now think about, and this is why it says transformations, think about what a negative on the front does to a function. What does it do? It flips it upside down. So my curve that normally looks like this is flipping upside down to look like this. Well, let me do that in a different color. Sure. So vertical asymptote, x equals 1. X-intercept, again, graph or center point, 2, 0. Domain is 1 to positive infinity, and range is all real numbers.